Welcome back, everyone, to the Deep Dive. Ready for another challenge? Today, we're going to see if we can understand something that's usually explained with some pretty dense equations.
Oh, yeah.
In a more elegant
and intuitive
way, right?
Right.
We're diving into the Demazure product.
Specifically in type D Coxeter groups.
Specifically in type D Coxeter groups. Now,
this usually involves reduced words.
Oh, yeah. The whole
shebang.
The whole 9 yards. But our source material hints at a more visual way to think about this.
That's right. The paper is called Demazure product and hopping in type D.
Demazure product and hopping.
Okay.
And what's fascinating here is this idea of hopping. Instead of getting lost in notation, they use hopping operators and one-line notation.
Hopping operators?
Yeah, to work with these products specifically for type D Coxeter groups.
So it's like finding a hidden shortcut through a mathematical jungle. I'm intrigued. Let's start with the basics. For those who might not be as familiar, what exactly are Coxeter groups?
Yeah, so why do we care about this Demazure product thing?
Coxeter groups are like families of symmetries, but with very specific rules.
Okay.
You can think about reflections that you see in a set of mirrors that are arranged in a particular way. Each arrangement kind of gives a different Coxeter group.
Okay.
The classic example is permutation groups. Those are type A Coxeter groups. And the Demazure product is a way to combine elements within these groups.
Gotcha.
And it pops up in representation theory, geometry, you name it.
Oh, wow.
It's a tool that connects a lot of areas.
So we've got these groups, ways to combine their elements, and this paper focuses on type D.
Right.
What makes type D special?
Type D, we're dealing with even-signed permutations.
Even-signed permutations.
So we've got permutations of numbers, but each number can be positive or negative, and there must be an even number of negative signs.
Right.
That evenness is really what sets type D apart.
Gotcha. So in type A, we might have something like 1, 3, 2, just a plain permutation. But in type D, it would be more like -1, 3, -2, because we need that even count of negatives.
Exactly. And these sign permutations can be represented in one-line notation, just like regular permutations. The paper leverages this notation to make things visually clearer.
So no more messy matrices or diagrams, just a line of numbers with signs.
That's the idea.
I can already see how that might make things easier to grasp.
Yeah, and remember, we can also unfold these sign permutations. We essentially attach a reversed copy with flip signs.
Oh, okay.
So -1, 3, -2 becomes -1, 3, -2, 2, -3, 1. This unfolding process is important for understanding how the hopping method works in type D.
Wait, so we're making the permutation longer as part of the process? That seems counterintuitive. Usually we want to simplify things, not make them more complex.
Yeah, it seems that way, right?
Yeah.
But the unfolding actually helps us see patterns and connections that would be hidden otherwise. It's like laying out all the pieces of a puzzle before you start putting them together.
Yeah.
You need to see the big picture.
Okay, I'm starting to get a sense of the landscape here. We've got these even sign permutations, this unfolding trick. But how does hopping fit into all of this? It still sounds a bit magical.
So hopping is where the visual intuition really kicks in.
Right.
Imagine you have a sign permutation written out in one-line notation.
Yeah.
A hopping operator tells you to swap certain elements based on a specific rule.
Okay.
It's like a little dance of numbers guided by these operators.
So we're not doing complex calculations, we're just moving numbers around based on these hopping rules.
Precisely. And the paper claims that by applying a specific sequence of these hopping operators, we can actually arrive at the Demazure product.
Really?
They found a way to encode that complex operation into these simple visual steps.
Okay, that's a pretty bold claim, but I'm guessing it's not as straightforward as it sounds, especially in type D.
Yeah, you're right. There are a few subtleties. Remember how type D requires an even number of negative signs? Well, when we opt in type D, we might end up with an odd number of negatives, and that's a no-no.
Ah, so we're playing this number swapping game, but we have this extra constraint to worry about. Sounds like it could get messy.
It definitely adds a layer of complexity, but that's what makes the findings of this paper so remarkable. They found a way to use hopping despite this challenge.
Okay.
Their main theorem states that for any two even-signed permutations, their Demazure product can be obtained by applying a sequence of hopping operators
Okay, hold on.
to their usual product.
We need to break that down a bit. We've got these two even-signed permutations. We calculate their usual product.
Right.
And then what? How do these hopping operators come in?
To figure out the right hopping sequence, we need to look at the unfolded version of the first permutation.
So the unfolded permutation is kind of like our guide.
That unfolded version gives us a blueprint, if you will, for constructing the hopping operators.
So it's like the unfolded permutation is a map, and the hopping operators are the steps we take to navigate that map.
That's a great way to put it. And each hopping operator is determined by two things.
Okay.
A starting position
Okay.
within the permutation and a list of numbers that guide the swapping process.
Wait, how do we choose those starting positions and lists? It seems a bit arbitrary. Is it just trial and error?
Not at all. The paper provides a very specific method for determining them.
Right.
It's based on something called the maximal parabolic decomposition of the first permutation, the one we unfolded.
Maximal parabolic decomposition.
Oh.
Okay, that sounds a little intimidating. Is this where we need a PhD in abstract algebra?
Don't worry, it's not as scary as it sounds. It's essentially a way of breaking down our permutation into simpler components.
Oh, okay.
Think of it like taking apart a complex machine to understand its individual parts.
Right.
Each part then dictates a hopping operator.
So each component of this decomposition gives us a hopping operator. And then we apply all these hopping operators, one after the other, to the usual product of our two original permutations. Right.
Exactly. And the amazing thing is that after applying all these carefully chosen hopping operators, the result we get is the Demazure product.
Really?
It's like magic,
Wow.
but with a solid mathematical foundation.
It's like they found a way to translate this complex algebraic operation into a series of simple visual moves.
Right.
I'm starting to see why you were so excited about this paper.
It's incredibly elegant, isn't it?
Yeah.
And it opens up a whole new way of thinking about the Demazure product.
So we've got our even sign permutations. We unfold the first one, break it down using this maximal parabolic decomposition thing.
Right.
And that gives us a set of hopping operators.
Yes.
We apply those operators to the usual product, and boom, Demazure product.
You got it.
Could I get that right?
You got it. Of course, there are a lot of details we need to unpack about how these hopping operators actually work.
Of course.
And how the decomposition dictates their structure.
Well, that's what we're here for, right? To dive deep into those details.
Exactly.
I'm ready to see how this hopping magic works in practice.
Let's take a look at an example.
Okay.
I think it'll become much clearer when we see the numbers in action.
Lead the way.
All right, let's get concrete. Say our two even-signed permutations are 1, 4, nagish 2, nagish 3, and 4, nagish 1, 2, nagish 3.
Okay.
Their usual product, just like combining regular permutations, works out to megish 2, megish 1, 4, 3.
Okay.
Still an even number of minus signs, as expected.
Okay, I'm following so far. We've got our usual product, but how do we get from there to the Demazure product using this hopping method?
Remember, we need to unfold the first permutation, 1, 4, nagish 2, negative 3.
Right.
Its unfolding gives us 1, 4, nagish 2, nagish 3, 2, nagish 1.
Okay.
This unfolded version will guide our hopping.
So we unfold the first permutation, but not the second one. Why is that?
That's right. The hopping operators will be acting on the usual product we already calculated.
Yeah,
Nagish 2, nagish 1, 4, 3. The unfolded permutation is just our roadmap for defining those operators.
Okay, that makes sense. So we've got our unfolded permutation and our usual product.
Right.
Now, how do we define these hopping operators?
Each hopping operator is like a little instruction set.
Okay.
It tells us which elements to swap, and we specify it with two things.
Okay.
A starting position
Okay.
and a list of numbers.
And how do we determine those starting positions and lists? It still feels a bit like pulling numbers out of a hat.
This is where the maximal parabolic decomposition comes in.
Right.
Remember how we talked about breaking down the first permutation into simpler components?
Uh-huh.
Each component gives us one hopping operator.
So this decomposition isn't just some abstract concept.
Right.
It actually gives us concrete instructions for how to hop.
Precisely. Let's look at our unfolded permutation 1, 4, and x2, next 3, 3, 2, next 4, and x2, 1.
Okay.
Without going into all the technical details, the maximal parabolic decomposition of the original 1, 4, negative 2, negative 3 gives us components that, in turn, translate to these hopping operators. h to the 3, negative 3, h4, 2, negative 2, and h6, 4, negative 4.
Okay, let's break that down. H2 means we're starting at position 2 in our usual product, which is the element minus 1.
Right.
What does the list 3, negative 3 tell us to do?
That list guides our hopping.
Okay.
We start at position 2. Scan the permutation to the right and look for the element from our list that's both furthest to the right and greater than our starting element, minus a 1. Remember, in type D, we have a specific ordering. 1, 2, 3, 4 by 4, nash 3, nash 2, 1.
Oh, okay.
Yeah.
So we're looking for either 3 or negative 3.
Uh-huh.
Since 3 comes after megas 1 in our ordering,
Right.
it's the one we choose. even though it's further to the left in the permutation.
Exactly. We swap -1 and 3.
Okay.
But because we're working with this unfolded idea in the background, we also swap their corresponding negatives, 1 and -3.
Okay.
So our usual product -2, -1, 4, 3 becomes -2, 3, 4, and -1.
Okay.
That's one hop completed.
So one component of the decomposition gave us one hopping operator,
Right.
which led to one swap.
Uh-huh.
We repeat that for each component.
You got it.
Okay.
Next up is H4 to -2, Henner to 4.
All right.
Starting at position 4, which is now go 1,
Okay.
we look for the element from our list that is furthest to the right and greater than 1 do. In this case, it's 2.
Okay.
So we swap -1 and 2, and they're -1 now, giving us -2, 3, -1.
I see. And we have one more hop.
Right.
H664, -4.
Uh-huh.
Our starting position, 6, is outside the length of our usual product. So this hop doesn't actually change anything.
That's right. Sometimes the decomposition leads to operators that don't result in the swaps.
Okay.
And that's okay. What matters is the final result. After applying all the hops, our usual product has transformed into -2, 3, -1, 2.
Okay.
Guess what?
What?
This is exactly the Demazure product of our 2 original permutations.
Oh, that's pretty neat.
Yeah.
We started with these seemingly abstract rules for hopping, and we actually arrived at the Demazure product. It's like a carefully choreographed dance of numbers.
And it's not just a coincidence. The paper rigorously proves why this method works. They establish a clear connection between the hopping operators, derived from the maximal parabolic decomposition, and the properties of the Demazure product in type D.
Speaking of the proof, can we delve into that a bit? I'm curious to see how they connect these visual manipulations to the underlying algebraic structure.
Absolutely. The proof is where things get really interesting. It hinges on a few key ideas.
Okay.
Remember that lifting operation we mentioned earlier?
A lifting, right.
That plays a crucial role.
It seemed a bit mysterious before, but you said it helps us manage the complexity of the unfolding.
Right.
How does it fit into the proof?
Think of lifting as a way to extract specific information from the unfolded permutation.
Okay.
It helps us keep track of the signs and ensures that our hopping actually leads to the correct Demazure product. The proof shows how lifting relates to the hopping operators and the properties of the Demazure product.
So lifting is like a behind-the-scenes mechanism that ensures that the hopping stays on track.
Exactly. It's a bit like having a stage manager who makes sure all the cues are hit perfectly during a performance.
Okay.
You don't see them, but they're essential for the show to run smoothly.
Okay, that's a helpful analogy.
Yeah.
So the proof connects the hopping operators, guided by the decomposition, to the Demazure product, with lifting playing a crucial role in ensuring everything works out correctly.
You got it. And the paper walks us through the key steps of the proof, showing how all the pieces fit together.
Okay.
It's quite intricate,
Yeah.
but ultimately very elegant.
I'm starting to appreciate just how much ingenuity went into this research.
Yeah.
They've taken a complex concept and made it accessible through this visual, intuitive approach.
It's a testament to the power of finding the right lens through which to view a problem.
Right.
Sometimes a visual approach can unlock insights that would be hidden in a purely algebraic framework.
This hopping method feels like a real game changer. It's like they found a secret passageway through a dense forest of symbols and equations.
And this is likely just the beginning. The paper hints at further research directions, like applying this method to even more complex structures like affine permutations.
So this is just the tip of the iceberg. There's a whole universe of mathematical structures out there that might be amenable to this kind of intuitive approach.
Precisely, and that's what makes this research so exciting.
Yeah.
It opens up new avenues for exploration and potentially simplifies our understanding of other complex mathematical concepts.
Well, I'm definitely feeling more enlightened about the Demazure product and this hopping method.
Good.
But before we get too carried away, I'm curious to hear more about the actual proof. What are the key ideas they use to establish this connection between hopping and the Demazure product?
Let's dive into some of the proof highlights.
Okay.
It's surprisingly accessible, even if you're not a seasoned algebraist.
Okay, good.
The key is to understand how the hopping operators interact with the structure of type D Coxeter groups.
Okay, lead the way. I'm ready to see how they connect the dots. Okay, proof highlights. I have to admit, usually when someone says proof, my eyes glaze over a bit, but you're making this sound surprisingly approachable.
Yeah, well, that's because the paper builds its argument in a really clever way.
Okay.
It doesn't just jump into some dense formula.
Right.
It starts by focusing on how hopping operators affect specific types of elements
Okay.
within these even sign permutations.
Okay, so instead of looking at the entire permutation at once,
Right.
they break it down based on the kinds of elements it contains.
Exactly.
Sort of like classifying the pieces
Yeah.
before figuring out how they move.
Exactly. They examine how hopping interacts with elements that are already in the correct order,
Okay.
elements that are out of order but have the same sign, and elements that are out of order and have opposite signs.
So they're essentially creating a taxonomy of how hopping behaves in different scenarios.
Right?
That seems like a smart way to manage the complexity.
It is, and by analyzing these cases individually, they can prove some key properties of the hopping operators.
Okay.
For example, they show that hopping preserves the parity of the permutation,
Okay.
meaning it always maintains an even number of negative signs, which is crucial for type D.
That makes sense. We talked earlier about how hopping in type D can lead to an odd number of negative signs,
Yeah.
which isn't allowed.
Right.
So the proof needs to demonstrate that their method avoids that pitfall.
Precisely. And they do that by showing that each hop, as defined by their method,
Okay.
either maintains the parity or flips the signs of two elements,
Okay.
ensuring the overall parity remains even.
So it's like a balancing act.
Exactly.
Every hop needs to keep that even-odd balance in check.
Exactly. And the paper meticulously proves that their hopping operators,
Okay.
derived from the maximal parabolic decomposition,
Okay.
always adhere to this balancing act.
That's impressive.
Yeah.
But how does this analysis of individual cases lead to a proof for the entire Demazure product? It seems like we're still looking at isolated moves, not the overall result.
That's where the lifting operation comes in.
Right, lifting.
Remember, lifting helps us extract specific information from the unfolded permutation.
Right.
The proof demonstrates that lifting plays a crucial role in connecting the local behavior of the hopping operators
Yeah.
to the global properties of the Demazure product.
So lifting acts as a bridge between the individual hops and the overall result.
Precisely. The paper shows that the lifting of the Demazure product can be expressed in terms of the lifted versions of the hopping operators.
Okay.
Essentially, lifting allows us to track how the hopping operators, step by step, transform the permutation into the Demazure product.
So it's like lifting provides a higher level view of the process,
Right.
allowing us to see the forest for the trees.
Exactly.
We can see how those individual hops, guided by the decomposition and kept in check by lifting,
Right.
ultimately lead us to the Demazure product.
Exactly. And the beauty of the proof is that it combines these visual, intuitive ideas with rigorous mathematical reasoning.
Yeah.
It's both elegant and insightful.
It's like they found a way to make the abstract concrete,
Yeah.
complex, simple. This hopping method is truly remarkable.
It is, and it has the potential to revolutionize how we approach other problems in Coxeter group theory and beyond.
Yeah, this deep dive has certainly opened my eyes to a whole new way of thinking about these concepts.
Good.
I used to see the Demazure product as this intimidating algebraic beast, but now I can visualize it,
Yeah.
understand it, and even appreciate its beauty.
That's the power of intuitive understanding. It transforms the way we see and interact with the world.
And it's a reminder that even the most complex mathematical concepts can often be understood in a more accessible, even playful way.
Precisely. And sometimes those playful approaches can lead to profound insights and breakthroughs.
Well, I think we've given our listeners a pretty thorough deep dive into this fascinating research.
I think
We started with the basics of Coxeter groups and the Demazure product, explored this innovative hopping method, and even delved into the key ideas of the proof.
Yeah, great work.
We've seen how a visual, intuitive approach can illuminate a complex algebraic concept and open up new avenues for exploration.
Yeah, for sure.
To our listeners, we encourage you to dive deeper into this topic. The world of Coxeter groups is full of fascinating patterns and symmetries waiting to be discovered.
Absolutely.
And who knows, you might even be inspired to find your own intuitive framework for understanding a challenging mathematical idea.
Yeah, that's the fun part.
Thanks for joining us on the Deep Dive. Until next time, keep exploring, keep questioning, and keep those mathematical minds engaged. Welcome back, everyone, to the Deep Dive. Today we're going deep into mathematics.
Oh, fun.
Yeah. We're exploring the Demazure product, specifically in type D Coxeter groups.
Okay.
So our source material is going to be excerpts from a research paper. And just a heads up to everyone listening, We are going to be assuming that you're already familiar with mathematical concepts and terminology.
Right. This is for the experts.
This is for the experts. So if it's
Go ahead, Doug.
if this is your first time listening to the deep dive,
Knife.
this might not be the episode for you, but if you are an expert, come dive in with us. And luckily, we have an expert right here to guide us through all this.
I'm going to try my best.
So the paper we're looking at today is titled Demazure Product and Hopping in Type D.
Catchy.
And the abstract sits the stage pretty well. It basically says that we're going to be extending a combinatorial description of the Demazure product using hopping operators to type D Coxeter groups.
Sounds exciting.
Yeah, I'm excited.
Demazure products are used all over in math, so finding efficient computational methods without relying on those abstract concepts like reduced words is super valuable.
Abstract stuff.
And this combinatorial approach using hopping operators, it's more intuitive, probably computationally advantageous.
So let's jump into the paper. The introduction starts by defining a Coxeter system, WS.
Standard.
And then goes straight into the Demazure product.
Right, and it uses the star symbol, the S, and it's defined on the Coxeter group W. It's like a monoid generated by elements of S.
Okay.
But SES equals S for any S in S.
So it's a little different.
Different from the typical group operation in the Coxeter group.
Gotcha.
And then...
Oh, and they connect the Demazure product to Bruhat intervals.
Right, in proposition 1.2.
Yeah.
It states that for any W and V in W, the lower interval E'd, WEV in the Bruhat order is a subset of the union of intervals E'd, X, where X is in id, WEIV.
So that suggests a way to decompose the Demazure product based on the Bruhat order.
Yeah, the Bruhat order helps us understand how elements are related in the Coxeter group based on reduced words.
Okay.
This proposition hints at a deeper connection between Demazure product and the structure of the group.
So the paper then goes into all this history of research on Demazure product, talks about different approaches, like using rank functions, almost sign-preserving permutations, and recursive methods with Monge matrices.
Wow, that's a lot.
Yeah, it's a lot, but they emphasize...
The paper is different.
Yeah, this paper focuses on the hopping operator.
Right, previously explored in types A and B, now they're going to extend it to D.
Exactly.
Which is harder.
Yeah, types A and B, pretty straightforward hopping operators, but type D, it's got different behavior under the unfolding operation, so it's a challenge.
So we know what the Demazure product is, how it connects to the Bruhat order, what the challenge is, what are we tackling in this paper?
Right, it's all set up.
So next we move on to section 2.
Where they revisit hopping operators in types A and B.
Right, lays the foundation.
The foundation.
Yeah, for type D.
Let's start with type A.
Okay.
So the symmetric group SN is a type A Coxeter group.
Classic.
With simple generators, S1, S2, all the way to SN1, representing adjacent transpositions. And they also introduce a new notation, WA.
Okay, this isolates a specific part of the permutation that's needed for the hopping operation.
And it removes elements smaller than a right.
It streamlines things, makes the definition cleaner.
Okay, now for the hopping operator in type A.
The heart of it.
It's denoted by HTL, and it acts on a permutation W.
You start at element T in W's one-line notation, scan right, looking for the furthest element in a set L that's larger than T.
Okay.
If you find one, you swap them and repeat until there are no more elements in L to the right of T.
They give us a good example here.
Oh, good.
For W91726435, and the hopping operator H1, 2, 3, 4, 5, 6, 7, 8.
Big one.
After applying the operator, we get 897625431 after a series of swaps.
And this seemingly simple operation connects to the Demazure product. Theorem 2.2, it states that for any permutations W and V, their Demazure product, WE, can be calculated by applying a specific sequence of these hopping operators to the usual product WV, a concrete way to compute the Demazure product.
So moving on to type B,
the
paper talks about sign permutations, which are permutations with plus or minus signs.
Adds complexity with the signs.
These form the type B Coxeter groups with Bn defined as a specific subgroup of the permutation group S2n.
Right.
Okay, so they define the unfolding of a signed permutation as writing out the permutation and then to its right, writing its reverse with signs flipped.
Like 4, -2, 3, -1 unfolds to 4, -2, 3, -1, -3, -4.
Yeah, exactly.
This helps us see how the hopping operator works.
It helps us visualize those symmetries inherent in the signed permutation.
Yeah, crucial for defining the hopping operator.
In a way that respects those symmetries.
Exactly.
So the hopping operator for type B, also denoted by HTL, operates on the unfolded sign permutation.
When swapping elements, we swap their negative counterparts too.
Right.
Keeps the sign structure.
So it's not just applying the type A operator directly.
Right, I got to maintain those properties of signed permutations.
Okay, so the paper gives an example for the other P mod of 4, 5, 3, mod of 4, not of 2, not of 6. Applying H1, not of 4, 3, 5, not of 6 results in mod of 4, 3, 5, mod of 2, minus a 6 after a few hops in its unfolded form.
And just like in type A, theorem 2.5 links the hopping operator to the Demazure product for sign permutations.
So the Demazure product of two sign permutations can be computed by applying a sequence of hopping operators to their usual product, but in their unfolded forms.
Unfolding bridges the gap between hopping operators and Demazure product.
Yeah, so we've seen how hopping operators work in types A and B.
The challenge,
Yeah.
extending them to type D.
Which is what we'll get to next time.
Yeah.
Okay, so last time we saw how those hopping operators work in types A and B.
Right, the setup for the main event.
Yeah, now let's tackle type D.
This is where it gets tricky.
Section 3 dives right into it. Talks about even signed permutations.
The ones with an even number of negative signs.
Those form our type D Coxeter groups.
And they don't embed as nicely into the permutation group as regular signed permutations do.
Through that typical geometric folding process.
Yeah, adds more complexity when you try to define a hopping operator.
So we need a different approach.
Combinatorial unfolding.
Okay, kind of like type B, but different.
It takes a signed permutation in a DN and creates a permutation in S2N.
Remark 3.2 points out that the relationship between the lengths of elements in DN and their unfoldings in S2N is different than in type B.
That's a big challenge.
Yeah, and example 3.4 really shows that.
Taking unfoldings, calculating the Demazure product in S8, and folding back doesn't even give us an even signed permutation.
So we can't just apply the type B approach.
We need a new method. Got to respect the structure of type D Coxeter groups.
Well, what do they do?
Maximal parabolic decomposition.
Sounds complicated.
It's just breaking down elements into simpler pieces.
Okay, so section 3.3 explains this.
Right, we focus on parabolic subgroups of Dn, specifically the maximal ones denoted Wj. You get those by removing one generator.
And then the elements of the right quotient, Wjs, are classified into 4 forms.
Which dictate how they act on even signed permutations.
We get a visual aid, too, with figure 2.
The Brouhat order of Wjs.
And example 3.5 shows how those forms affect the one-line notation.
Form 1 elements, they cyclically shift entries, but keep the signs the same.
Form 2, they shift and flip signs at specific spots.
And Form 3, well, they're more complicated, affect the one-line notation differently.
But Corollary 3.6 says that A and Y element in Dn decomposes into a product of these forms.
Like building blocks.
Yeah, so this decomposition helps us define the hopping operator.
It gives us a system to handle those different forms and how they affect even signed permutations.
So in section 4, we finally get to defining the hopping operator for even signed permutations.
And showing how to use it to compute the Demazure product in DNN.
This is where it gets interesting.
Yeah, the authors did some really clever work here.
So the definition is similar to type B, operates on the unfolded even signed permutation.
But remember, it doesn't always stay within the even signed permutations.
They give an example where you apply H1, 3, 1, 2 to 1, 5 and get a 3, negative 4, 2 and get 2, 5, and negative 1, negative 4, and negative 3.
Odd number of negative signs, not in DeFi anymore.
So they have to be careful, kind of make sure they stay within even signed permutations when applying this operator.
They do a careful analysis of how the operator interacts with those different forms of elements.
Leads to their hopping transfer proposition.
Proposition 4.6 is the key. It says that if you have a building block, chi, from the decomposition and apply it to an even signed permutation W, you can get the same result by applying a specific hopping operator to chi W.
So it links Demazure products and hopping operators in type D.
It's proven through a series of lemmas, each one dealing with a different form of key.
Lemma 4.2 for form 1, lemma 4.4 for form 2, lemma 4.5 for form 3.
They establish the exact relationships between those chis and the hopping operator.
Those proofs are important, show that the relationships actually hold.
Solid math behind the main result.
And they use line to represent that ordered list in the hopping operator for each key.
Keeps things concise, easier to work with.
So then they introduce this lifting operation.
It extracts information from the unfolding of an even signed permutation.
Denoted by WGA.
Takes the subword of WE's unfolding strictly left of I, but only entries in II.
So you're focusing on the relevant parts of the unfolding.
Yeah, the parts we need for the hopping operation.
And then they show how lifting connects to hopping operators.
For example, lemma 4.8 shows that if J and J are next to each other in the hopping operators list, you can swap their positions without changing the outcome.
This simplifies things, streamlines the proof of the main theorem.
Highlights the symmetries within the operator and how it interacts with unfolding.
Then they introduce an equivalence relation I to group lists that produce the same result when used in a hopping operator with index I.
Elegant way to handle variations in the operator's input.
So they really understand that underlying structure, distilling those complex relationships.
And Lemma 4.10 shows that the order of elements in the decomposition from corollary 3.6 doesn't matter when using lifting in a hopping operator.
As long as the overall structure is the same.
This is a key step towards proving the main theorem, shows that lifting captures a fundamental property.
Suggests that the hopping operator with lifting can work independently of the decomposition details.
Makes it a more powerful tool.
Okay, so we've got lifting, and we know its properties, so where do we go from here?
To the star of the show, proposition 4.11.
Okay.
It links the lifting operation, hopping operators, and decomposing an element in D-in.
So it's the connection to the main theorem.
Exactly.
Okay, so what does this proposition tell us?
It says we can express that ordered list using lifting applied to a specific part of the decomposition.
So like translating.
Yeah, between hopping operators and decompositions.
And that's how we finally express the Demazure product using hopping operators.
You got it. Leads us to theorem 4.1, the culmination of all this work.
It says that the Demazure product of two even-signed permutations, we can calculate it by applying a sequence of hopping operators to their product.
But those lists in the hopping operators come from the lifting operation.
So instead of all that abstract stuff, we've got a concrete way to compute the Demazure product.
Using hopping operators and lifting.
Amazing.
And the paper doesn't just state the theorem, it proves it step by step.
So they start with the Demazure product expressed using those keys.
And apply the hopping transfer proposition, then proposition 4.11, to transform it into those hopping operator.
Each step builds on the previous one, nice and elegant.
And they give us an example too.
To solidify it.
They take two even sign permutations, W2 and X4 minus 1, 5, 3, and V equals 4, 3, minus 5, minus 1, and X2,
Okay.
and show how to calculate their Demazure product using theorem 4.12, walking through each hopping operator application so we can see how it works.
Really breaks down from this complex operation to these intuitive hopping movements.
That's the power of combinatorics.
So we took this abstract structure.
And found a concrete way to represent it, to work with it.
Shows how beautiful math can be.
It really does.
So we started with Coxeter groups, explored the Demazure product,
Ran into those type D challenges.
and saw how they solve them with hopping operators and lifting.
But this paper does more than just solve a problem.
It opens up more research.
Like that open question about extending hopping operators to affine permutations.
Lots to explore there.
It's a whole new map for us to chart.
So even for math experts, why should we care about these hopping operators and the Demazure product?
Because Coxeter groups are everywhere. Algebra, geometry, even physics, they help describe symmetries.
And the Demazure product shows how those symmetries interact.
Right, so having an efficient way to compute it, like with hopping operators, gives us a powerful tool.
To analyze those symmetries.
And the insights we get from Coxeter groups, they have applications outside pure mathematics too.
Like in computer science, economics, physics.
Even the most abstract math can have a real impact.
Well, it's been a pleasure diving into the world of Coxeter groups with you. And all you listeners out there, we encourage you to check out the paper yourself, see what else you can discover. Until next time, keep exploring. Welcome back, everyone, to the deep dive.
Yeah.
Excited for today. We're taking a deep dive into a paper all about the Demazure product,
Oh, yeah!
specifically in type D Coxeter groups.
Sounds very exciting.
It is. You know, this product, it just seems to pop up everywhere.
It really does.
Like from rep theory to geometry, you name it.
Mm-hmm.
But calculating it, it can get so messy,
It can be a headache.
especially when you're wading through all those reduced words, the Brouillard order.
Right, and it's easy to get lost in the weeds there.
Exactly. But the authors of this paper, Han, Huang, Keller, and Zhang,
Quite the team.
they've developed this really elegant approach using something they call the hopping operator.
Very clever.
Yeah. And it's this visual, intuitive way to compute the Demazure product. But get this, using just one-line notation.
So you can just bypass all that complexity.
Exactly. No more getting bogged down in the weeds.
Love it when a plan comes together.
Me too. But before we get into their type D innovations, I think a little refresher would be helpful.
Always a good idea.
For our listeners, can you give us a quick recap of what the Demazure product is and why it's so important?
Absolutely.
I know our listeners are familiar, but it never hurts.
Of course, of course. So the Demazure product, you often see it with a star symbol. It's basically an associative operation on a Coxeter group.
Okay.
You can think of it as like a way to combine elements in the group, but in a way that respects a certain order, the Bruhat order.
Right. The Bruhat order.
Yeah.
That's what tells us about the complexity of the elements.
Exactly. You got it.
So the Demazure product, is it giving us like the most complex combination possible?
In a way, yes. It's all about finding that most complex combination within the constraints of the Bruhat order.
Interesting. So because of this connection to the Bruhat order and the whole associative property, the Demazure product ends up showing up in all sorts of interesting areas, right?
Oh, absolutely. It's everywhere. For example, in representation theory, it helps us understand how certain modules are structured. And then in geometry, it pops up when you're studying Schubert varieties. Those are these geometric objects tied to Coxeter groups.
Right. Fascinating stuff.
It really is.
Okay, so that's a great reminder of why this product is so important, so versatile.
Sure.
But now let's get to the hopping operator. How does it actually simplify all those calculations?
Well, the idea was first introduced for types A and B Coxeter groups. And it's all about bringing a more visual combinatorial approach to computing the Demazure product.
More visual. I like that.
It's much easier to grasp.
Yeah. So maybe let's start with type A. That's the one that deals with permutations, right?
Exactly.
Can you give us like a concrete example? It's something our listeners can really sink their teeth into.
Absolutely. Let's take the permutation, say, W will 42153.
Okay, 42153.
Got it. Now, the hopping operator itself, it's denoted by H with a subscript T and a set L.
Like HTL.
That's the one.
Yeah.
Now, that subscript T, that represents an element from the set 1, 2, up to N, where N is the length of the permutation.
Okay.
And L, that's an ordered subset of the same set.
So for our example, 42153, we could pick, say, T2 and L equals 3, 5.
Perfect example.
All right, I'm following so far.
Great. Now, to actually apply this hopping operator, we start at the position of T in our permutation, which is position 2 in this case, and we scan to the right.
To the right, okay.
And what we're looking for is the furthest element in L that's greater than T. So in our example, that would be 5.
5, right.
And then we swap T with that element.
So our permutation becomes 4, 5, 1, 2, 3.
Exactly. And
Yeah.
we just keep repeating this process, scanning and swapping, until there are no more elements of L to the right of 2.
So in this case, we're done. We already hopped over the only element in L greater than T.
Precisely. We're done with this hop.
That's it. Seems pretty simple.
It is, and that's the beauty of it. This hopping operator lets us compute the Demazure product without getting lost in reduced words or the Bruhat order.
Right. So in type A, the Demazure product of, let's say, 2 permutations, W and V, can be calculated by just applying a specific sequence of these hopping operators to their usual product, WE. It's like a recipe. Hop here, hop there, boom, you have the Demazure product.
Exactly. A recipe for mathematical success.
I like that.
Much easier to visualize than all those reduced word manipulations.
Definitely. And you said this extends to type B as well, right? Signed permutations.
Yes, it works nicely for type B, but we started talking about type D. That's where things take a turn.
What makes type D so different?
Well, type D is also about signed permutations, but there's a catch.
Okay.
It only includes those with an even number of negative signs.
So interesting.
And this little difference, it throws a wrench in the works.
How so?
The technique of unfolding signed permutations, it works like a charm for types A and B,
Okay.
but it completely breaks down in type D.
Unfolding. Can you explain that a bit? Some of our listeners might not be familiar.
Of course. So imagine you take your signed permutation and you create a mirrored copy of it, but you flip the signs.
A mirrored copy, flipped sign.
Yeah, and then you just stick them together.
Okay, I'm picturing it.
So for example, if you had the signed permutation -2, 1, noisule 3, its unfolded version would be -2, 1, -3, 3, -1, 2.
Okay, so you double the length and flip the signs in the second half.
Exactly. Now, in types A and B, you could analyze the Demazure product of these unfolded permutations and then just fold the result back to get the Demazure product of your original signed permutations.
Clever. But that doesn't work in type D.
Nope. Because this unfolding, it can create permutations with an odd number of negative signs.
Oh, I see. And those aren't allowed in type D.
Exactly. So the authors had to find a whole new way to define the hopping operator for type D.
A whole new way.
Yep, they had to make sure it always kept that even sign condition intact.
That sounds like quite the challenge.
It was.
So how do they adapt the hopping operator to handle this constraint? How do you make sure you always have an even number of negative signs?
Well, that's what we'll delve into next time. They had to get pretty creative to solve this puzzle.
Can't wait to hear it. So how did they pull it off? How did they modify this hopping operator?
Well, they came up with a clever tweak to the whole hopping process, just to make sure it kept that even sign property.
A tweak.
Yeah, let's illustrate it with an example.
Okay, I like examples.
So let's say we have the even sign permutation. Let's call it W equals 4, 5, 3, minus 1, minus 2, minus 6.
Minus 4, 5, 3, minus 1, minus 2, minus 6.
Exactly. And let's say we want to apply the hopping operator H1L to this.
Right.
Where L, our hopping set, is the ordered set minus 3, 4, minus 5, 6.
Well, I got our even sign permutation and our hopping set all set.
So what's the first step?
Well, we unfold our permutation, right? Like we did before in types A and B.
Right. So unfold, W is going to be -4, 5, 3, -1, -6, 6, 2, 1, -3, -5, 4.
Okay, so we've mirrored it, flipped the signs, the whole shebang.
Now we got to find our starting point, right?
Which is 1 in the unfolded permutation.
Exactly. And from there, we scan to the right, looking for the furthest element in L that's bigger than 1.
So in this case, it's -5.
Right. So naturally, we'd want to swap 1 and -5.
But wouldn't that mess up our even sign condition?
Aha. That's the trick.
Okay, I'm intrigued.
To keep that even sign condition, whenever we swap elements that have opposite signs, we also got to swap their negatives.
Oh, that's smart.
So here, we swap 1 and I to 5, but to compensate, we also swap -1 and 5.
Makes sense. So our unfolded permutation now becomes -4, -1, 3, 5, -2, -6, 6, 2, -5, -3, 1, 4.
Yeah, you're getting the hang of this.
I'm trying.
Okay, so we successfully hopped 1 over -5, kept our even signs, all good.
What next?
Well, we repeat the process, right? Scan to the right of 1 again.
Okay.
This time we find 4 in our set L, which is bigger than 1.
Swap time.
Exactly. Swap 1 and 4.
Do we need to swap their negatives too?
Not this time. 1 and 4, they've got the same sign.
Right. We only swap negatives when the signs are opposite.
Exactly. So after this hop, our unfolded permutation looks like -1, -4, 3, 5, -2, -6, 6, 2, -5, -3, 4, 1.
So we've hopped 1 over all the elements in L that are bigger than it.
Yep, we've reached the end of L.
So what?
Now we fold it back. Just take the first half.
Back to our original size.
Exactly. So the result of applying H1, -3, 4, -11, 5, 6 to our original permutation is
-1, -4, 3, 5, -2, -6.
spot on.
So to recap, we unfold, we hop while keeping those signs balanced, and then we fold it back.
Exactly.
It's elegant. A bit more intricate than types A and B, but still.
It's the price we pay for type D.
Fair enough.
And this is the basic dance, if you will, for each hopping operator in the sequence. The one that defines the Demazure product in type D.
Right. And the subsets L, those are determined by that first permutation in the product.
That's right, just like we saw in types A and B.
So it's like following a recipe, but the ingredients are these hopping operators and even sign permutations.
I like that analogy.
This hopping operator adaptation, it's definitely clever, but did they actually prove that it really calculates the Demazure product correctly in type D? That's got to be the big question.
Absolutely. And that's where the real ingenuity shines through. They used this adapted hopping operator with something called maximal parabolic decomposition to really nail down their main result.
Maximal parabolic decomposition.
Sounds intimidating, I know.
Oh.
But think of it like breaking down a giant puzzle into smaller bite-sized pieces.
Okay. I could work with that.
So it lets you express any element in type D as a product of elements from these subgroups that have a simpler structure, you see. And the authors, they use this decomposition to analyze the Demazure products step by step.
So like, okay, let's zoom in on each little piece and see how it behaves with the hopping operator.
Precisely. It's all about understanding the local behavior to get the global picture.
Like they've created a roadmap to navigate the wilds of type D Coxeter groups.
Exactly. And by carefully examining each step on this roadmap, they showed that this new hopping operator, it truly captures the essence of the Demazure product in this setting.
Very cool. But before we get too lost in the weeds of their proof, can we maybe walk through a concrete example from the paper?
Of course. Seeing it in action is always helpful, right?
Definitely. It'll help our listeners get a better feel for how it all works in practice.
Let's take a look at their example using the permutations W equals 2, -4, -1, 5, 3, and V equals 4, 3, -5, -1, -2.
All right, I'm ready to see this hopping operator do its thing. All right, let's dive into those base cases for the hopping transfer proposition.
Okay, so remember, there are 3 main parts to this proposition, right? Each one deals with a different form of that element key, the one from the maximal parabolic decomposition.
Right, breaking it down.
So the first form 1, that's the easiest one.
Okay.
It deals with elements that look like key equals psi.sj.
Okay.
where ILN1.
So those are like chains of those simple transpositions.
Exactly. The most basic building blocks.
So what does the hopping transfer proposition actually say about this form?
It says that for this kind of chi, the Demazure product, chi UW, it's the same as applying the hopping operator, HII plus 1, AJ plus 1, to the usual product key.
So in simpler terms, we're hopping the element at position I over all those elements from I plus 1 up to J plus 1.
You got it. It's a very visual way to think about it.
Okay, that makes sense intuitively. But how do they actually prove that this hopping gives you the right Demazure product?
Well, their proof is a great example of mathematical induction, which is a really powerful tool.
Wait, induction, yeah.
They start with the simplest case, where J equals...
So key is just a single transposition, say.
Exactly. That's their base case.
Solid foundation. Start with the basics.
Now, the interesting thing is they actually already proved this specific case in a previous paper, the one focused on types A and B.
Oh, so they're building on their previous work.
Exactly. It's all connected.
A smart move.
The proof for that base case, it involved a lot of careful analysis of how the hopping operator HII plus 1 affects the order of the elements in the permutation.
Okay.
And they showed it produces the same result as taking the Demazure product of C and W.
Got it. So they have a solid proof for that simplest scenario.
They do. But what happens when J is bigger than I? When we have a longer chain of transpositions?
Yeah, that's where it gets more complicated, right?
That's where the inductive step comes in. That's the heart of the proof.
His inductive step, okay.
So they assume that the proposition holds for key plus 1 SI plus 1 SJ.
They assume it works for a shorter chain.
Exactly. And then they show that it must also hold for key equals psi that SJ.
Okay, so they're like, if it works for this shorter chain, it has to work for the longer one too.
Precisely. It's all about building up from the base case, step by step.
Clever. So how do they actually make that jump from the shorter chain to the longer one?
The key is that they use the associative property of the Demazure product.
Associativity. Always a handy tool.
Right. So they express key W as psi EA, Q plus 1 EAW.
Okay, I see what they're doing. They're isolating that Q plus 1 that they already know how to handle.
Exactly. Because remember, we assumed the proposition holds for Q plus 1.
Right. So they can apply the hopping transfer proposition to that part of the expression.
That's the beauty of it. So now they can replace that Demazure product, QI plus 1 EA, with a hopping operator applied to Q plus 1 E.
Okay, they've swapped out a Demazure product for a hopping operation.
And from there, they use what they know about hopping operators and simple transpositions to just manipulate the expression, do some mathematical gymnastics.
I see.
And through a series of very careful steps, they show that this whole thing can be simplified to HI, I plus 1, AJ plus 1 key.
Which is exactly what the hopping transfer proposition says it should be for this key.
Bingo. So they've essentially shown that if it works for the shorter chain, it has to work for the longer one as well.
It's like a domino effect, proving it one step at a time.
Exactly. The power of induction.
Okay, so we've covered form 1, those chains of transpositions.
Now, forms 2 and 3, those get a bit trickier because they involve that special transposition.
Right, Serien, the one that flips the signs.
That's the one. And that adds a whole extra layer of complexity.
So how do they handle that added complexity?
Well, the core idea is the same. Break it down into base cases and then use induction.
Okay, same strategy, but more delicate steps.
Exactly. They have to be very careful because of that sign flipping.
Can you give us an example of how they deal with that sign flipping in one of those more complex forms?
Sure. Let's look at form 2. Those are elements like key si.sn blocks dash kicker snsn-1.sj or iaj an1.
So agen is right there in the middle of the chain.
Yep, smack dab in the middle, causing mischief.
And what does the hopping transfer proposition say about this form?
It says that for this form, you can get the Demazure product key EW by applying the hopping operator HII plus 1 NNJ plus 1 to key.
Wait, so now the hopping set has both positive and negative numbers.
That's right. That's because of the sign flipping action of sin.
It's like sin is reaching across the whole permutation, affecting everything.
It's powerful stuff.
So how do they even prove this? Where do they start?
The base case for this form is really interesting. They have to break it down even further into 2 subcases. One where J 8 RHI and another where J Li plus 1.
Okay, so they're getting really granular here, examining every possible scenario.
Exactly. They have to be super thorough to make sure the sign flipping doesn't throw everything off.
What techniques do they use to actually handle the sign flipping in those subcases?
It's a combination of things. They do a lot of case-by-case analysis where they look at every possible arrangement of elements and see how the hopping operator behaves.
Okay, so a lot of meticulous checking and double checking.
And they also use some clever tricks with the hopping operator itself, adjusting it in specific ways to make sure the signs stay balanced.
So they're really fine-tuning those hopping operations to work perfectly with Snap.
Precisely. They're making sure the hopping operator plays nice with the sign flipping.
And once they've got those base cases nailed down, how do they extend it to the more complex scenarios?
Just like before, they use induction. They assume the proposition holds for a simpler Q hat plus 1, and then use that assumption to prove it for chi.
So they're building up their arguments step by step, just like with Form 1.
Exactly. But again, they have to be extra careful because of that sign flipping.
Yeah, it's like walking a tightrope, making sure those signs stay perfectly balanced.
It is. They have to keep track of all the sign changes that sign introduces and adjust their hopping sets and operations accordingly.
So it's like they're choreographing a dance, where the hopping operators and sign flipping have to move together in perfect harmony.
I love that analogy. It's a delicate dance indeed.
Okay, so they've proven the hopping transfer proposition for Form 2, and I assume Form 3 follows a similar pattern.
Exactly. Form 3 deals with elements that look like chi, psi.sn2sn, so psi n is at the very end.
Right, yeah.
And the proof involves the same careful consideration of base cases and induction, all while keeping a watchful eye on those sign changes.
It's incredible how much detail goes into proving something like this.
It's a testament to their rigor and dedication, for sure.
So by meticulously proving this proposition for all three forms of chi, they've essentially created a complete guide to understanding the Demazure product in Type D, right?
Exactly. They've built a solid framework for working with this product in this very specific setting.
And that framework leads them to their main theorem, the one that says the Demazure product in Type D can be fully expressed through these hopping operators.
It's a beautiful result. It takes something that could be quite abstract and gives us a concrete visual way to think about it.
It's amazing how they've managed to bridge that gap between abstract algebra and this intuitive visual process.
It really highlights the power of mathematical insight.
This has been an incredible journey. We've gone from the basic definition of the Demazure product all the way to the intricacies of hopping operators in Type D.
It's been quite the deep dive.
And we even got to peek behind the curtain and see how they built their proof step by step.
It's always fascinating to see how mathematicians put these intricate arguments together.
It is. It gives you a whole new appreciation for the elegance and rigor of mathematics.
Absolutely. And it inspires us to keep exploring, to see what other mathematical mysteries we can unravel.
That's a great note to end on. Well, that's all the time we have for today's deep dive. We hope you enjoyed exploring the fascinating world of the Demazure product and hopping operators with us.
It's been a pleasure.
And until next time, keep those mathematical minds curious and keep exploring. Welcome to the deep dive. Today, we're diving deep into Coxeter groups and something called the Demazure product.
Oh, fun!
Yeah, we've got a fascinating paper to unpack that tackles this product in Type D Coxeter groups using a tool called the hopping operator.
Mm-hmm.
It sounds pretty abstract, but trust me, it gets really interesting.
It does. Before we jump into the hopping, maybe we should take a step back for our listener and explain what these things even are.
Right.
You encounter Coxeter groups in a surprising number of mathematical areas. They capture essential ideas of symmetry and have applications in geometry, algebra, and even combinatorics.
Right. It's like this underlying structure that pops up everywhere.
And it is, yeah.
And this paper is focusing on a specific operation you can do within these groups, the Demazure product.
Exactly.
Yeah.
It's also sometimes called the zero Hecke product.
Okay.
And it has connections to a bunch of other interesting mathematical concepts, like the Bruhat order, Schubert variety, and even things like subword complexes.
Oh, wow.
What's really neat about this paper is that it builds on previous work where they figured out a way to calculate this Demazure product using this hopping operator for types A and B Coxeter groups. And now they're extending it to type D, which is way more challenging.
Okay, I'm intrigued.
Yeah.
So the listener sent in this paper, and it looks like the authors are very clear about their goal right from the abstract. They're trying to extend this combinatorial approach, this hopping method, to calculate the Demazure product specifically for type D Coxeter groups?
They are. It's all about finding elegant ways to calculate this product without getting bogged down in complex algebraic manipulations.
So before we get to the hopping,
Yeah.
let's take a moment to define what this Demazure product actually is.
Okay.
Could you give us a formal definition?
Absolutely.
Right.
Formally, the Demazure product, denoted by the symbol A,
Okay.
is an associative operation defined on a Coxeter group. A Coxeter group W has a generating sets
Okay.
and relations of the form. It's seps n's e's, where s and h are elements of S, and eps is a positive integer or infinity.
Okay, I'm trying to picture this.
Yeah.
So we have these generators S and T, and they're kind of like the basic building blocks of our group.
Exactly.
And these relations tell us how we're allowed to combine and rearrange these building blocks.
Exactly. They govern the interactions between these generators.
Okay.
For example, if emps is 2 for a particular pair of generators, S and 8, it means if you apply S followed by T twice, you'll end up back where you started at the identity element of the group.
Okay, I see.
Yeah.
So where does this Demazure product fit into all of this?
Right.
How is it different from just regular multiplication in the group?
That's a great question. It actually follows the same braid relations as the Coxeter group,
Okay.
meaning it respects the same underlying structure.
Mm-hmm.
However, there's a key difference. Instead of the relation that we have in the Coxeter's group of
But
it.
through the Demazure product, we have S E series. S equals S.
Interesting. So it's like a modified multiplication rule that still captures the essence of the Coxeter group structure, but with a slight twist.
Yeah.
Now, the paper mentions that this Demazure product has a nice interpretation in terms of something called the Bruhat order.
Right.
Can you remind us what that is?
Of course.
Yeah.
The Bruhat order is a way to partially order the elements of a Coxeter group.
Mm-hmm.
You can visualize it as a kind of hierarchy within the group
Hi.
where some elements are considered greater than others based on how they can be constructed from the generators.
Okay, so it's like a ranking system within the group.
Right.
And how does the Demazure product relate to this Bruhat order?
There's a key property that connects them
Okay.
for any two elements. W and Sherry V in our Coxeter group.
Mm-hmm.
Their Demazure product, WV, will always result in an element that's greater than or equal to both W and Sherry in the Bruhat order. So in a way, the Demazure product gives us an element that's sort of like the least upper bound of the two elements we're multiplying, if we're thinking in terms of this Bruhat order hierarchy.
That's a great way to put it.
Okay.
And this property is really powerful because it links the Demazure product to other important concepts like Bruhat intervals
Right.
and helps us understand the structure of Coxeter groups in a deeper way.
This is already fascinating.
Yeah.
But before we get too deep into the theoretical weeds,
Okay.
can you remind us why we should care about the Demazure product in the first place?
Right.
Where does it actually show up in other areas of mathematics?
You're right. It's not just a theoretical curiosity.
Yeah.
It pops up in a surprisingly diverse range of mathematical fields.
Mm-hmm.
For example, in algebraic geometry,
Okay.
the Demazure product helps us understand the structure of Schubert varieties, which are these special geometric objects associated with Coxeter groups.
Okay.
And in combinatorics, it plays a role in the study of subword complexes, which are built from the generators of a Coxeter group.
Wow. So it really is a concept with far-reaching connections.
It is, yeah.
Okay. I think we've got a good grasp of the basics now.
Okay,
Let's dive into the heart of this paper, the hopping operator.
let's do it.
Can you walk our listener through how this hopping idea was first developed for types A and B Coxeter groups?
Absolutely. Let's start with type A,
Okay.
which deals with permutations.
Permutations. Those are a bit easier to visualize, right?
Yes,
Like shuffling a deck of cards.
exactly. In type A,
Yeah.
we can represent these permutations using one-line notation.
Okay.
For example, 891726435 represents a permutation of the numbers 1 through 8,
Right.
where they've been rearranged in that specific order.
Okay.
Now, the hopping operator acts on these permutations
Okay.
based on a chosen number T and an ordered subset L of our numbers.
Okay, so we pick a number from our permutation.
Yes,
And subset of the numbers, and then we do some hopping based on that.
exactly.
I'm curious, what does that hopping actually look like?
Imagine you're scanning the one-line notation from left to right,
Okay.
starting at your chosen number T.
Mm-hmm.
The hopping operator tells you to find the furthest element to the right that is both in your subset L and larger than T.
Okay.
If you find one, you swap T with that element.
Okay.
Then you repeat this process until there are no more elements in L to the right of T that are larger than it.
So it's like our chosen number T is hopping over certain numbers in the permutation,
Yes.
always moving to the right, and only swapping with elements that are both larger than it and belong to our chosen subset L.
Precisely.
Okay.
And the incredible thing is that by applying a sequence of these hopping operators, carefully chosen based on the permutations you're working with, you can actually compute the Demazure product.
Wow.
There's a theorem in the paper that formally states this relationship between the hopping operators and the Demazure product.
Wait, so you're telling me that by just doing these simple swaps, this hopping, we can figure out the Demazure product?
Yes.
That's pretty mind-blowing considering it's connected to all these other complex mathematical concepts.
It is pretty amazing. The paper even provides a concrete example to demonstrate how this works. They take the permutations, W of 6541723 and V 5436217, and show step by step how applying the hopping operators, as defined in their theorem, leads you to the correct Demazure product.
Okay, so they've shown that hopping works beautifully for permutations in type A.
Yes.
What about type B?
Right.
How do they extend this idea?
Type B Coxeter groups deal with signed permutations, which are like permutations, but with an added layer of complexity. Each number can be either positive or negative.
So it's like our deck of cards analogy.
Yeah.
But now some cards might be face up and some might be face down.
Exactly.
That adds an interesting twist.
That's a great way to visualize it. To handle these signed permutations, the paper introduces this neat trick called unfolding. Essentially, they transform a signed permutation into a longer permutation by adding a reversed copy with flipped signs.
I see. So they convert the signed permutation into a regular permutation.
Right.
And then can they apply the same hopping idea as in type A?
You got it. They modify the hopping operator slightly to take into account the signs of the numbers. But the core idea remains the same. And they prove another theorem, showing that a carefully chosen sequence of these modified hopping operators applied to the usual product of two signed permutations gives you their Demazure product.
So there's this beautiful parallel between types A and B.
Yes.
They both have this elegant hopping structure underlying the Demazure product.
Exactly.
But now we come to the heart of the paper. Type D.
Right.
Didn't they hint that extending the hopping approach to type D is not as straightforward?
They did. Type D Coxeter groups deal with even signed permutations. These are a special subset of signed permutations where there's an even number of negative signs. And as the paper points out, this unfolding trick that works so well in type B doesn't behave quite as nicely for type D.
Oh, so there's a twist.
Yes.
We can't just rely on the same tricks from type B.
No.
I'm really curious to see how they handle this challenge.
Me too. This is where their ingenuity shines through. But before we dive into that, let's take a closer look at what makes type D unique. Starting with how we represent these even signed permutations.
Let's unpack that. How are even signed permutations different?
Even though they're a subset of signed permutations, the way we represent them in one-line notation and how these simple transpositions act on them have some subtle differences. The paper carefully explains these nuances, using a clear example to illustrate how we obtain the one-line notation for an even-sided permutation by applying a sequence of simple transpositions.
Right. It's all about how we swap elements and change their signs within this one-line notation. But the rules are a bit different because we need to maintain an even number of negative signs.
Exactly. And this difference plays a crucial role in why unfolding doesn't translate directly from type B to type D. The authors highlight this with a remark, pointing out that the way we measure the complexity of permutations using something called length is not always preserved when we unfold even signed permutations.
So this neat trick of unfolding, which helped us move from type B to type A, breaks down when we try to apply it to type D.
Precisely. And they don't just tell us, they show us. They give a specific counterexample with two even-signed permutations. One for magnitude 3 and 4, magnitude 1, 2, negative 3, and show that if you try to unfold them and calculate their Demazure product as regular permutations, you get an incorrect result that doesn't even belong to the type D Coxeter group.
Wow, so unfolding leads us down the wrong path in type D.
Yeah.
Does this mean the hopping idea is doomed?
Not at all. Instead of giving up, they get creative and introduce a powerful tool called maximal parabolic decompositions. Think of it as a way to break down these type D permutations into smaller, more manageable pieces that are easier to work with.
I'm intrigued. It sounds like they're taking a divide and conquer approach.
Exactly.
But before we get lost in these decompositions,
Okay.
maybe it's a good time to switch gears and pick up the story in our next segment.
Yeah, that sounds good.
What do you think?
Sounds good to me. Let's give our listener a moment to digest all this before we delve into the world of maximal parabolic decompositions and how they connect to hopping in type D.
Okay.
Welcome back. We left off talking about how unfolding, which worked so well for signed permutations in type B, hits a snag when we try to apply it to even signed permutations in type D.
Right. They showed us a concrete example where unfolding led to a completely wrong answer for the Demazure product.
Yes.
So what do? Do they abandon the hopping idea altogether?
Not at all. They're determined to make hopping work in type D, even if it requires some new tools and techniques.
Okay.
And that's where these maximal parabolic decompositions come in.
Okay, you've piqued my curiosity. What are these maximal parabolic decompositions and how do they help?
Think of it like this. You have a big, complex puzzle, and to solve it, you break it down into smaller, more manageable pieces. These decompositions do something similar for even signed permutations.
Okay.
They allow us to break down each permutation into a product of simpler elements, each belonging to a special subgroup called a maximal parabolic subgroup.
So it's a strategy for simplifying the problem by dissecting these type D permutations into smaller building blocks.
Exactly. And the paper goes into detail about how these decompositions work, providing a visual guide to the structure of these subgroups. They even classify the elements of these subgroups into 4 distinct forms.
Can you give us a more concrete example of how these decompositions look and how they're helpful?
Of course. Let's revisit the running example with the even signed permutation 2, meta 4, meta 1, 5, 3 fund. They show how each of these 4 forms of elements, when multiplied by this permutation, transforms it in a specific way. It's like watching these permutations rearrange themselves according to a set of rules dictated by the decomposition.
That's a great way to visualize it.
Yeah.
It's like they're giving us a set of tools for manipulating these permutations based on their decomposition.
Precisely. And the beauty of it is that they prove a corollary. Showing that any type D element can be broken down into a product of these simpler elements, each coming from one of these maximal parabolic quotients. They even demonstrate this with their running example, showing exactly how it decomposes.
I see the strategy now. They're creating this framework for dissecting these type D permutations into their fundamental components. But how does this connect back to the hopping operator? That's the part I'm really eager to understand.
That's where the real magic happens. They've laid out this elegant system for decomposing type D permutations. And now they're going to show us how the hopping operator can be used to navigate this system and ultimately compute the Demazure product.
Lead the way. I'm ready to see how they pull this off.
Let's move to section 4, where they formally introduce their hopping strategy for type D. They start by defining the hopping operator for even signed permutations. And you'll notice that the definition itself looks very similar to the one for type B.
So the hopping operator itself doesn't change. But the way it behaves in type D is different because of those tricky even signed permutations.
You got it. Remember how we talked about unfolding not playing nicely with the Demazure product in type D? Well, that difference in behavior also affects how the hopping operator interacts with these permutations. Specifically, when you apply the hopping operator to an even signed permutation, there's no guarantee you'll end up with another even signed permutation.
Oh, that sounds problematic.
It is.
If the hopping operator can take us outside the world of even signed permutations, how can we use it to calculate the Demazure product, which is supposed to stay within that world?
That's the challenge, and the authors address it head on. They even provide an example to illustrate this issue. They take the even signed permutation 1, 5, madish 3, madish 4, 2 fit, and apply a specific hopping operator to it. As they walk us through the steps, we see that the result 2, 5, madish 1, madish 4, nash 3 fit has an odd number of negative signs, meaning it's no longer an even signed permutation.
So the hopping operator can lead us astray in type D. It seems like this hopping idea might be a dead end. What do they do?
This is where their deep understanding of the interplay between hopping and those maximal parabolic decompositions comes into play. They prove a series of lemmas and propositions that establish specific rules for how the hopping operator interacts with the different forms of elements from their decomposition.
So they're figuring out the rules of the road for hopping in type D, taking into account how it interacts with the building blocks of their decomposition.
Precisely. They meticulously analyze how hopping affects each form of element from their decomposition, showing how it transfers through the hopping operator and modifies the hopping list in predictable ways. And they provide clear examples to illustrate each case, making sure we can follow along with their logic.
Okay, so they're building up a toolbox for hopping in type D,
Right.
understanding its nuances and potential pitfalls.
Yes.
But we're still missing the connection to the Demazure product.
Right.
How do they bridge that gap?
They introduce a clever concept called lifting,
Okay.
which allows them to salvage a useful piece of information from the unfolding process,
Okay.
even though the full unfolding itself isn't directly applicable in type D.
So they're not completely abandoning unfolding,
Right.
but they're extracting a specific part of it that's still helpful in type D.
Exactly. They define this lifting operation very precisely and then prove a lemma, showing that under certain conditions, swapping the order of a number and its negative within the hopping list doesn't change the outcome of the hopping operation.
Okay.
It's a subtle but crucial detail that will play a key role later.
Okay, I see how they're carefully piecing together the rules of hopping in type D,
Yes.
taking into account the unique properties of these even-signed permutations.
Exactly.
But how do they connect this back to the Demazure product?
Right.
I'm on the edge of my seat.
They're setting the stage for a grand finale. They prove another lemma, showing that certain lifted elements from their decomposition behave the same way when used in hopping operators, even though they might have different forms.
Okay.
It's like they're finding hidden equivalences within the structure of those decompositions.
So they're uncovering these subtle connections between hopping, lifting, and those decomposition elements.
Yes.
It sounds like they're getting close to cracking the code of the Demazure product in type D.
You're absolutely right. All their work culminates in Theorem 4.2,
Okay.
where they finally reveal their elegant formula for expressing the Demazure product using hopping operators. Are you ready to see how it all comes together?
I'm all ears. Let's hear this grand theorem.
All right, get ready for the grand reveal. Theorem 4.12 states that for any two even sign permutations, phi and w, their Demazure product d and w, can be calculated by applying a specific sequence of hopping operators to the usual product of v and w.
Okay, at first glance, that sounds pretty straightforward.
Yeah.
But knowing this paper, I'm guessing there's more to it than meets the eye.
Right.
Can you break it down for us?
You're right. There's a lot of intricate machinery working behind the scenes. The theorem is essentially saying that you first multiply v and w together using regular permutation multiplication.
Right.
Then you apply a sequence of hopping operators to the result, and what you get is magically their Demazure product.
Wow.
The clever part is that the specific hopping operators you need are determined by those lifted elements we talked about earlier.
Right.
The ones that capture key information from the maximal parabolic decomposition of W.
So it's like those lifted elements are acting as a guide for the hopping operators.
Yes.
Telling them exactly how to transform the regular product into the Demazure product.
Exactly.
That's pretty neat.
Yeah.
But didn't you say the proof relied heavily on that decomposition?
It does.
Even though the final theorem doesn't explicitly mention it?
Exactly. That's what makes this result so elegant. It's like they use the decomposition as a scaffolding to construct the proof.
Yeah.
And once the theorem was standing strong,
Yeah.
they gracefully removed the scaffolding, leaving behind this beautiful and concise statement.
Okay, color me impressed. I'm dying to see how they pull this off. Can we walk through the proof?
Absolutely. The proof is beautifully structured like a well-choreographed dance. It starts by recalling that W can be decomposed into a product of those simpler elements.
Right.
The cheese from the maximal parabolic decomposition.
Mm-hmm.
They then use that hopping transfer proposition we discussed earlier.
Yeah.
This allows them to rewrite the Demazure product, EW, as a series of hopping operators applied to these individual key elements.
So they're essentially breaking down the Demazure product into smaller, bite-sized pieces that can be handled by these hopping operators.
Precisely. And then, through a series of clever manipulations, they use their propositions about lifting and those equivalence relations they establish to transform this expression step by step.
Right.
And wouldn't you know it, they arrive at the exact form stated in the theorem. A sequence of hopping operators applied to the usual product of V and W. It's a masterful display of mathematical deduction.
Wow. It's amazing how they managed to navigate the complexities of type D and uncover this hidden hopping structure underlying the Demazure product. But let's be honest, seeing is believing.
Yeah.
did they provide a concrete example to show this theorem in action?
Of course. They wouldn't leave us hanging.
Okay, good.
They take the even-signed permutations, W2 minus 4, 9, 1, 5, 3, and V equals 4, 3, minus 5, minus 1, minus 2, which we've encountered before,
Right.
and show us exactly how to calculate their Demazure product using their hopping formula. They carefully demonstrate each step, applying the hopping operators in the precise sequence dictated by the theorem.
Right.
And what do you know? The result matches the Demazure product calculated directly.
That's so satisfying. It's like watching a magic trick unfold.
Right.
But instead of smoke and mirrors,
Yeah.
it's pure mathematical elegance.
It really is. This paper is a testament to the power of creative mathematical thinking. The authors didn't just solve a problem, they took us on a thrilling journey, guiding us through their reasoning, showing us the obstacles they faced, the tools they invented, and the key insights that led to their remarkable result.
And they didn't stop there. They end the paper with a question that's sure to spark the curiosity of any mathematician.
Right.
They ask, can one come up with hopping operators for affine permutations to describe the Demazure product? It's like they're throwing down the gauntlet,
Yeah.
challenging us to extend their work to an even more abstract and complex setting.
What an inspiring way to end this deep dive.
Yeah.
It reminds us that mathematics is not just about finding answers.
Right.
It's about asking new questions, exploring uncharted territories, and constantly pushing the boundaries of our understanding.
A huge thank you to our listener for sending in this fascinating paper. And to all our listeners out there, keep exploring, keep questioning, and keep that mathematical fire burning. Until next time, happy diving.
Yeah.
All right, let's dive into some pretty intense math today.
Yeah.
We're going to be tackling the Demazure product, specifically in type D Coxeter groups.
Right.
You know how it can sometimes feel like you're navigating a maze but blindfolded?
Right.
Well, this paper gives us a brand new map. It's kind of a visual way to find our path, and they call it hopping.
Yeah, it's really quite elegant, actually. The paper that we'll be exploring today is Demazure product and hopping in type D by Han, Huang, Keller, and Zhang. And they present this new method for calculating the Demazure product using just the one-line notation of a permutation.
So no more messing around with those crazy reduced words.
Exactly, yeah. It streamlines things considerably.
Okay, well, that's a relief. So before we jump into the specifics of type D, can you give us like a super quick refresher on what the Demazure product is itself and why it's so important?
Absolutely. So the Demazure product is also known as the zero Hecke product, and it's an operation that's defined on Coxeter groups. And Coxeter groups are these really fascinating objects that have connections to a bunch of different areas in math, like geometry and representation theory.
Yeah, I remember them popping up when I was studying Lie algebras.
Exactly, yeah. So you can think of the Demazure product as like a way to combine elements in these Coxeter groups in a specific structured way.
So it's not just your typical multiplication then?
Yeah, not quite, no. It's defined using the generators of the Coxeter group, and it relates to something called the Bruhat order.
Okay.
Which is basically a way to partially order.
Right, the Bruhat order. It's like a family tree for permutations showing which ones are like greater or smaller in a certain sense.
That's a great analogy. And the Demazure product interacts with this order in really interesting ways.
Okay.
Now, to understand this hopping method, we need to first look at how it works for like simpler types of Coxeter groups. So like types A and B.
Sounds good. Let's start with type A. I remember those are basically the groups of permutations of a set of objects, like shuffling cards.
Precisely. And the hopping operator for type A, it involves like systematically swapping numbers within the permutation based on their position and value.
Okay.
In the one-line notation.
Okay. I think I can visualize that. It's like systematically rearranging the cards in the deck.
Exactly, yeah.
What about type B? Those are the ones with the sign permutations, right?
Yes. In type B, each number in the permutation can have a plus or minus sign attached to it.
Okay.
And the hopping operator in this case works with what's called the unfolding of the signed permutation.
Okay.
Which basically represents it as a permutation of a larger set.
So we're basically kind of extending the permutation to include the negatives of the numbers as well.
Exactly, yeah.
Yep.
And the hopping operator acts on this unfolded permutation.
Okay.
And now, here's where things get interesting.
Okay.
While hopping works really well for types A and B, applying it to type D presents like a unique challenge.
Oh, why is that?
Well, type D Coxeter groups, they're represented by what's called even-signed permutations, so those with an even number of negative signs.
Okay.
And the way we unfold these permutations in type D is different from type B. And it turns out this unfolding doesn't always preserve the Bruhat order.
Ah, so that really throws a wrench in things. If the order's not preserved, our usual hopping techniques
Exactly.
might not work as we expect.
Precisely. And that's the main problem that this paper addresses. They came up with a really clever way to modify the hopping method to take into account this difference in type D.
Okay, I'm very intrigued. So let's delve into the specifics of type D and see exactly how they tackle this challenge.
Okay.
So the paper starts by introducing the type D Coxeter group and its diagram.
Yes, and they use a specific convention for the diagram, which is something to keep in mind as we go through the details.
Okay.
They also clearly define the one-line notation for type D, focusing on those even-signed permutations
Yep.
we talked about.
And they even explain how simple transpositions, those swaps of adjacent elements,
Yeah.
act on these even sign permutations.
Yeah.
And they connect those actions to the one-line representation.
Yes.
I was like when they give those concrete examples.
Absolutely. The examples make it so much clearer.
For sure.
Now, like we mentioned, the main difference in type D is its combinatorial unfolding. It's different from the type B unfolding.
Right.
And the paper really highlights this difference in remark 3.2, where it states that the length order is not always preserved by this unfolding in type D.
So simply applying the type B hopping technique wouldn't work directly.
Exactly. And example 3.4 demonstrates this perfectly.
Right.
They show that unfolding type D permutations and applying the type A Demazure product doesn't always give you a valid type D permutation.
So we need a new strategy.
Yeah.
What was their approach?
So to get around this, they introduce what's called maximal parabolic decomposition for type D.
E-composition. So we're breaking down these type D elements into smaller, simpler pieces.
Exactly. And they define 4 specific forms for the elements in this decomposition, labeled 0 through 3.
Okay.
And they give concrete examples of how each of these forms act on the right of an even-signed permutation.
Right. And those examples really help visualize the process.
Yes, the examples are key. And the important result here is corollary 3.6, which states that any element in a type D Coxeter group can be decomposed into a product of these specific forms.
So it's like we have a set of building blocks that we can use to construct any element in the group.
Precisely. And this decomposition is really the foundation for their modified hopping method.
All right. So we've laid the groundwork with the decomposition.
Yeah.
Now, how do they bring hopping into this whole picture?
So that's where section 4 comes in. They reassure us that despite the challenges that we have with unfolding in type D, the hopping operator can still be used to compute the Demazure product.
Okay.
The key is to apply it strategically in conjunction with this decomposition.
Okay. I'm ready to see how this all plays out. Where do they start?
So they start by emphasizing that the type D hopping operator is actually defined identically to the type B one.
Oh, okay.
So the mechanics of hopping itself are the same, but the context in which we apply it is more nuanced.
Okay.
And they caution that hopping in type D might actually result in a permutation that is not an even-signed permutation.
So it might temporarily fall outside of our type D group.
Right, exactly. That's an important point to remember. And then they present a series of lemmas that explore how hopping interacts with these different forms from our decomposition.
So they're analyzing how hopping behaves when we apply it to those specific building blocks.
Exactly. It's like figuring out the rules of the game for combining hopping with these particular types of elements.
Okay, let's go through those lemmas one by one.
Okay.
What's that first one about?
So lemma 4.1 focuses on simple transpositions, but excluding a specific one that they denote as SN.
Okay.
And this lemma shows that for these transpositions, hopping in type D kind of behaves similarly to types A and B.
So in those cases, the unfolding issue doesn't cause a problem.
Right, not for those specific transpositions. And they give a concrete example to illustrate how the hopping operator works in this context.
Makes sense.
Yeah.
What about the other forms from the decomposition?
So lemmas 4.2, 4.3, 4.4, and 4.5 each address one of the specific forms.
Okay.
Demonstrating how a sequence of particular transpositions interacts with the hopping operator.
So they're systematically analyzing how hopping interacts with each type of element from our decomposition.
Precisely. And for each lemma, they give an illustrative example, which is super helpful. To keep things organized, they actually introduce the notation Li
Okay.
to represent the specific list that's used for the hopping operators in each lemma.
So LA encodes the specific sequence of transpositions we're applying in each case.
Exactly. It's a shorthand way to represent those hopping lists. Then they take a big step forward and they combine all of these individual lemmas into proposition 4.6,
Okay.
which they call the hopping transfer proposition.
So this proposition brings together all those rules for how hopping interacts with those different forms.
Exactly. It provides a very concise way to express how each form, chi, those elements from our decomposition, interacts with the hopping operator. It's like a master key that unlocks the hopping behavior for all those building blocks.
Okay, I'm starting to see the bigger picture here.
Good.
We've analyzed how hopping interacts with each piece of the decomposition.
Yes.
What's next?
Okay, so now they introduce a really crucial concept called lifting in definition 4.7.
Okay.
Lifting extracts some specific information from the unfolding of a type D permutation that is relevant to hopping.
So lifting helps us bridge the gap between the unfolded permutation and the hopping operation.
Exactly. And they provide an example to illustrate how lifting actually works. Then we have lemma 4.8, which is called the hopping negation lemma.
Okay.
And this lemma allows us to swap j and disj in a hopping list under specific conditions.
So it addresses a kind of symmetry in the hopping operator where the order of j and j may not matter?
Precisely.
Yeah.
And they illustrate the impact of this swapping with an example as well.
Nice.
Then comes definition 4.9, which introduces an equivalence relation that is denoted by I.
Dope.
This relation basically captures the idea that different lists can actually lead to the same hopping result. It's like recognizing that there might be multiple paths to the same destination.
Ah, so we're grouping together those different hopping lists that have the same effect on the permutation.
Exactly. And this equivalence relation is key to simplifying how we understand hopping.
This is all coming together so beautifully. What happens next?
Okay, so then they delve into this really nuanced relationship between those decomposition elements, key,
Okay.
and lifting. And this culminates in lemma 4.0.
Okay.
And this lemma states that while the lifting might be different between the steps of the decomposition,
Okay.
they actually behave equivalently when used in hopping operators.
So even though the individual liftings might look different at each step, they'll eventually lead to the same hopping result.
Exactly. And of course, they provide an example to illustrate this point.
Of course, of course.
All right, so next, they connect all of these pieces together with proposition 4.11.
Okay.
And this proposition links that hopping list, L,
Right.
to the lifting of the decomposed permutation.
So it shows how those specific hopping lists that we defined earlier are related to the liftings of the elements from our decomposition.
Exactly. And they provide a detailed example to show how this connection works in practice.
This has been quite a journey. We started by defining hopping in those simple types, and now we understand how it interacts with the decomposition of these type D elements and their liftings.
Yes.
Are we finally ready for the main result?
We are. All of this has led us to theorem 4.12, titled Demazure product in type D as hoppings. This theorem states that we can express the Demazure product in type D purely in terms of hopping operators that are applied to the one-line notation.
Wow, that's incredible. They actually achieved their goal of finding a visually intuitive way to compute the Demazure product in type D. No more reliance on those crazy reduced words or abstract representations.
Exactly. And what's really remarkable is that even though the proof relies on that intricate decomposition that we just explored,
Right.
the final result itself doesn't, which is amazing.
Right.
It's a testament to the power of finding elegant solutions in math.
Absolutely. I can't wait to see this theorem in action. Do they provide any examples?
They do. They illustrate theorem 4.02 with a concrete example, calculating the Demazure product using hopping operators.
This is so exciting. I feel so much more comfortable with the Demazure products in type D now, thanks to this hopping method.
It is a really powerful tool.
It is.
But there's so much more to explore. Are you ready to delve into those specific examples that they provide to illustrate the theorem?
Absolutely. Let's jump into those examples and see exactly how this hopping method plays out in practice.
Okay. Welcome back. I'm ready to see these examples.
Me too. It's one thing to understand a theory, but seeing it applied to actual cases really makes it click.
For sure.
Where do we start?
Okay, so let's start with example 4.13.
Okay.
They have this permutation in D5, W2, 4, 1, 5, 3.
Okay.
And the goal is to compute the Demazure product of this permutation with itself W egg.
Okay, so we're basically like squaring this permutation
Yeah.
using the Demazure product.
Yeah.
How do they approach this with hopping?
So remember that idea of lifting we talked about?
Right.
So they start by calculating the liftings of W with respect to each index from 1 to 4.
Right. Those liftings extract the information that we need for each hopping operator. So W1 would be 2, -4, 5, 3, -5.
Right.
W2 would be -4, 5, 3, -5, and so on.
Precisely. They list out all 4 liftings,
Okay.
and then they very carefully apply the hopping operators one by one, using those liftings to guide them.
It's like they're choreographing this dance of permutations with each hopping operator rearranging the elements.
Yeah.
So what's the final outcome?
So after applying all 4 hopping operators, H4, H3, H2, H1,
Okay.
each guided by the corresponding lifting, they get 8, 3, 4, 2, 1, 5.
Nice. We computed the Demazure product of W with itself.
Yes.
Just using hopping. No crazy algebraic manipulations needed.
Exactly. It shows how elegant and efficient this method is.
Very much so.
Yeah.
Okay, that was impressive. What other examples do they have?
Okay, so example 4.14 brings in a slightly different scenario.
Okay.
They have 2 different permutations in D5. W2, 4, 4, 1, 5, 3, and V4, 3, 5, 1 on 2.
Okay.
And this time the goal is to compute WEV.
So instead of scaring a permutation, we're combining 2 different ones
Right.
using the Demazure product.
Exactly.
Does this change our hopping approach at all?
So the basic idea is the same.
Okay.
We still compute the liftings of W
Right.
with respect to each index.
Okay.
But this time, instead of applying the hopping operators to W itself,
Right.
we apply them to that product WV.
Right. So they first calculate that usual product WV, which
Right.
gives 5, 1, iridu, 3, 4.
Right.
And then they apply the hopping operators, again, H4, H3, H2,
Yeah.
H1, using the corresponding lifting of W as the guide for each one.
Exactly.
Okay, and so what's the final result after we do all that hopping?
They end up with 1, 3 of 4, 2, 5.
Another successful application of hopping.
Yes.
I really like how visually intuitive this is.
Yeah.
You can almost picture these elements hopping around
Right.
based on those lifting lists.
It is a powerful way to think about it. Okay, so then example 4.15 looks at a more specific case
Okay.
where they compute the Demazure product of a permutation with a simple transposition, SASCF.
Ah, yes, those simple transpositions, the building blocks of our Coxeter group.
Right.
I wonder how hopping simplifies things in this case.
Well, they show that you actually only need a single hopping operator to compute the result.
Wow, that's a lot of simplification.
Right.
Why does it work out so nicely?
So they explain it by connecting it back to the properties of the Demazure product itself.
Okay.
And how those simple transpositions act as generators of the Coxeter group. Since we're essentially multiplying by one of those building blocks, a single hop captures that action.
So it's like we're taking a single hop along a specific path within that group structure.
Exactly.
Makes sense. So what's the final example?
Okay, so example 4.16 takes us back to that Bruhat order.
Right, the family tree of permutations.
Exactly.
How does hopping tie into that?
So they have this proposition that shows how hopping can actually be used to figure out if one permutation is less than or equal to another one in the Bruhat order.
So we're not calculating the Demazure product, but using hopping to answer a different question about these permutations.
Exactly. The proposition states that if we can transform one permutation into another through a sequence of hopping operators, then the first permutation is less than or equal to the second one in the Bruhat order.
So we're hopping along the branches of that family tree,
Yeah.
moving from one permutation to another.
Right.
And if we can find a hopping path, it tells us about their relative positions in that Bruhat order.
Exactly. And they illustrate this with an example in D4, showing how we can hop from one permutation to another, revealing that Bruhat order relationship.
This is really cool. It's like hopping has given us these new tools to explore not just the Demazure product, but also the structure of Coxeter groups themselves.
It really shows the versatility and the depth of this approach.
I'm so impressed by how this paper has presented the Demazure product in Type D. They made what could have been a very abstract and complex topic so accessible through this hopping method.
I completely agree. It's a great example of the power of finding the right way to look at a math problem.
Yeah, and these examples have really helped me understand. I feel like I could actually apply this hopping method now.
That's great.
It's always rewarding when these concepts finally click.
It really is.
But we're not done yet. The authors wrap up the paper with the conclusion,
Right.
reflecting on their findings and talking about future directions.
Right.
I wonder what they say. Do they point towards any open questions or new avenues to explore?
Yes, they do, and we'll talk about that in the last part of our deep dive.
Okay, so we've reached the final part of our deep dive into Demazure product and hopping in type D. This hopping method has completely changed how I think about these structures. It's so elegant and intuitive.
Yeah, it's really remarkable how such a simple concept like hopping can unlock so much about these mathematical objects.
Right. So as we wrap things up, where do the authors kind of leave us? What are their final thoughts, and what about future directions for this research?
So they start by summarizing their main achievement,
Okay.
which is that they successfully developed a method for computing the Demazure product
Right.
for type D Coxeter groups,
Right.
using only that one-line notation of permutations.
No more getting bogged down in those reduced words and all that. That's a huge win for clarity.
Absolutely. And they emphasize that this method is not just some trick, but it's really like a framework
Right.
that shows us something fundamental about the structure of these groups.
Yeah, the analysis of that maximal parabolic decomposition and the lifting, those were both crucial to making this hopping method work for type D.
Absolutely. Those were key insights that allowed them to figure out how to deal with that unique unfolding thing in type D Coxeter groups.
Right, right. I'm curious, do they point towards any open questions or future directions for this research?
They do. They bring up a really interesting question about extending this hopping method to affine permutations.
Affine permutations, those are permutations of like an infinite set, right?
Yes.
That sounds really complex.
It does. It's like a whole other level.
Mm.
But it's a natural next step because if this hopping approach can bring so much clarity to finite Coxeter groups, then maybe it can also help us understand those really intricate affine permutations as well.
Yeah, that would be exciting.
Hmm?
I imagine that such an extension would require a lot of clever new ideas and adaptations.
It would, for sure. But it could be really groundbreaking. Affine permutations are important in so many different areas of math, and a visual tool like hopping could be a game changer.
I'm also wondering about applications of this work in other fields.
Hmm.
Remember how we talked about the connection between Demazure products and things like representation theory and algebraic geometry?
Of course. The ability to compute these products efficiently using this intuitive hopping method could lead to new discoveries in those fields as well.
It's so cool to think about the impact of this work across different areas of math.
Yeah, it really highlights how interconnected mathematical ideas are. Often a breakthrough in one area leads to all these unexpected advances in others.
This whole deep dive has been a perfect example of that. We started with hopping,
Right.
and it's led us to a much deeper understanding of not just the Demazure product, but also Coxeter groups and how they relate to so many other mathematical concepts.
And hopefully it's inspired our listeners to explore these ideas further.
Oh, I have no doubt about that. This paper has been such a great example of how math research can be both rigorous and elegant and complex, but also accessible.
I agree. And who knows, maybe one of our listeners will be the one to tackle that open question about affine permutations and take this hopping method even further.
The future of mathematics is full of possibilities.
It is.
All right, we'll wrap up this deep dive into Demazure product and hopping in type D. This has been such a great journey.
It has.
Thank you so much for joining us. And until next time, keep exploring, keep questioning, and keep hopping.
Yes, absolutely.